when you design these circuits, actually when you design high-speed circuits, communication circuits, these are always in the form of ICs. Therefore, when we are discussing, I will be telling about, or I will be speaking about the technology that is used. For example, I will say that 0.18 micron device. So there we mean that the technology used is for designing a device whose size is 0.18 micron. And then the characteristics of the device are accordingly set. Depending on the size of the device, the characteristic of the device changes. Once the characteristic changes, then the property or the behavior of the device will change. So if you are getting a broadband, you may get a narrow band, or you may broaden the bandwidth. So that will affect the bandwidth. Again, that will affect the gain, and that will affect how much bias you can give to the device, depending on the size of the device. Because the larger the size, the more current it can dissipate, the more power it can take. The less the size, the less power it can take. So it will burn out if you give more power. So there is restriction on biasing voltage, etc. So you should know these things beforehand, but we are going to discuss these things during the course of our discussion on the device. So let me continue with the broadband amplifier, its design example. We'll try to see the design example of a broadband amplifier, simple design examples. On that we'll try to see. Hopefully you have got the books, textbook or reference book that we discussed in the first class. Also, you have got the notes from the website. From this website, you have got the notes. You have read. You are trying to read the notes. You are trying to read the textbooks. If you have doubts, please ask me, or in the department you can contact Dr. Narayan Sahu. He will clarify your doubts definitely in the department. Otherwise, you can ask me. I will try to clarify your doubts on this paper. There will be doubts, no doubt there will be doubts. On that I understand, and we can handle those doubts definitely. There should not be a problem in handling those doubts. So now let us start with this, the issue of velocity saturation in the design of this MOSFET amplifier. Most of the time we assume that the MOS current, the current in the MOS current, when we say MOS current, we mean it is ID, the drain current. MOS current is the drain current. So the drain current is a quadratic function of voltage between the gate and source. So gate source voltage, its quadratic function. The form of this current is IDA is equal to constants mu o n COX is the capacitance, by 2 W by L into VGS minus VT whole square. Since it is VGS minus VT whole square, so we say that ID is a quadratic function of VGS. Now this VGS minus VT whole square we can write as VGS minus VT into VGS minus VT. So one of these VGS minus VT, for that we can write VD sat for a fixed length. So VD sat means the saturation voltage at the drain. So drain saturation voltage for a given length. So VG sat L, that corresponds to the saturation voltage at a given length. Length means the channel length in the MOS. So which we can also say in some books you will see that it is delta V. So ID is equal to mu COX upon 2 W upon L, VGS minus VT into VSAT, VD sat L or delta V. VD sat L also can be written as VGS minus VT. When we have strong inversion, below velocity saturation, velocity, below the velocity saturation, if you have strong inversion, then VD set L is approximately equal to VGS minus VT. That is why we are writing this. So this equation, the second equation, is applicable or is valid only under the case of strong inversion. When inversion is strong below the velocity saturation, then the second equation is valid, otherwise the first equation is valid. Okay. Now let us continue with the saturation velocity. What is velocity saturation? Before going into that, note that when you consider MOSFET, in MOSFET, when electrical field is along the channel and the electrical field along the channel reaches a critical value, the velocity of the carriers, in this case mostly the electrons, they tend to saturate. So the velocity of the carrier is, you are taking n-type, then the electrons, they will tend to saturate. Velocity will tend to saturate, which means velocity will no more increase, it will saturate, so it will remain constant. Once it saturates, then the mobility degrades. Because it has remained constant, so mobility will not increase, so mobility will degrade. This saturation, this is what is called saturation velocity. The saturation velocity of electrons and holes, both are carriers for n-type and p-types, electrons and holes are carriers. This is approximately 107 cm per second. So now you can show this relation. VD sat, you can find an expression for VD sat, VD or saturation velocity is approximately equal to VGS minus VT into LE sat by VGS minus VT plus LE sat, where L is the channel length, but E sat is the lateral electric field which is along the channel. So lateral electric field at which the saturation velocity occurs. E sat is the electric field, lateral electric field, where this is occurring, the saturation velocity occurs. Now you can see in the equation on right hand side we have written VGS minus VT parallel LE sat. Why we have written like that? Because you know, if we take two resistors R1, R2, they are in parallel, then the equivalent resistance for two resistors is R1, R2 by R1 plus R2. This equation, the middle portion is in that form. If you take R1 to be VGS minus VT, R2 to be LE sat, then that is in that form. Therefore, we are writing it as VGS minus VT parallel LE sat. Okay. Now, in this equation, suppose you have VGS minus VT by L much smaller than E saturation. So if that occurs, and the VGS minus VT by L is much smaller than E saturation, then VG sat or the saturation voltage will be approximately equal to VGS minus VT. That you can see from the above equation, you can put that VGS minus VT by L is much smaller than E saturation, or VGS minus VT is much smaller than L times E saturation if we multiply both sides with L times E saturation, and then you can neglect the E saturation there in the numerator, and in the denominator will be neglected. It will be approximately equal to LE saturation, that you will cancel out with the LE saturation in the numerator, because VGS minus VT is much smaller than LE saturation. In the denominator will become LE saturation. Now LE saturation in the denominator, LE saturation in the numerator, they will cancel out, leaving out V saturation. So VD saturation is approximately equal to VGS minus VT. Now in the other case, second case is VGS minus VT by L is approaching E saturation. So it is approximately equal to E saturation. So if that is there, if that approaches E saturation, then the quadratic equation is no longer valid here. In this case, quadratic equation will be no longer valid, because the numerator will be, suppose R1 R2 in the form R1 R2. So R1 R2 by R1 plus R2. Now R1 is approximately equal to R2, equal to R, let us say. Numerator is R square, denominator is 2R, so that is becoming R by 2. So there is no quadratic expression. So quadratic equation is no longer valid. Now the last case is VGS minus VT by L is much greater than L saturation, LE saturation. So in that case, the equation will be in the denominator, we will neglect LE saturation compared to VGS minus VT. So that goes out. Then VGS minus VT in the numerator and denominator will cancel out once you neglect LE saturation in the denominator. So that will leave out VD saturation is approximately equal to LE saturation. Since L is constant, therefore VD saturation will be constant. Therefore, IV characteristics will become linear. Since VD saturation is constant, IV characteristics will become linear. So we have seen three conditions, three cases. In the first case, we keep the quadratic equation. In the second case, quadratic equation is no longer valid. Third case, IV characteristic becomes linear because VD saturation is a constant. And now let us look at the modeling of the device in saturation velocity. When we are considering velocity saturation, there we consider the device modeling. Suppose L is small, like today's device, all the devices now we are trying to get to the nanoscale, so the channel length is small. The smaller, the better. That is what we see. And if L is smaller, then it will be high speed, definitely, because you have small length to cover. So suppose L is small, then velocity saturation is going to impact us or impact the design for even moderate values of VGS minus VT. And even with VGS minus VT, small values or moderate values of VGS minus VT, with that also the velocity saturation is going to have an impact. For that, look at the expression for ID. ID is equal to mu n C0x by 2 W by L into VGS minus VT into VD saturation. Now VD saturation we have seen. VD saturation is VGS minus VT parallel LE saturation. So ID is equal to the first equation that we see. Now this is approximately equal to mu n C0x by 2, that remains as it is. Then W by L, from the W by L, we will get VGS minus VT parallel LE saturation. That is when VGS minus VT is moderate, as we have seen, when VGS minus VT is moderate and it is negligible compared to LE saturation. Under that condition, the ID saturation is equal to LE saturation. So if you put LE saturation there, numerator and denominator we have L, that will cancel out, leaving out EG saturation, which means that ID will increase linearly with VGS minus VT. So small change in VGS minus VT is going to give a change in ID because it is increasing linearly. Depending on the slope of that will be mu n C0x by 2W into E saturation. So this is the equation of a straight line with a slope mu C0x by 2W into E saturation. So ID and ID is a function of VGS minus VT. Now under this condition, find out what is the transconductance. Transconductance in velocity saturation. Gm is the transconductance, and how you define Gs? It is the differentiation of ID or the current and then current with respect to the gate to source voltage. So Gm is equal to dID by dVGS. Now that we can easily find out since we know what is the expression for ID. So take the differentiate it with respect to VGS. So dID by VGS, everything is constant. Mu is constant, C constant, W constant, E constant, 2 constant, VT constant. So VGS minus VT, when you take differentiate it with respect to VGS, that will give you 1. So leaving out Gm is equal to mu C0x W or E saturation divided by 2, or Gm is equal to mu n C0x by 2 W into E saturation, which means this is the transconductance is no longer a function of VGS. VGS is gone. It is no longer a function of VGS, which means the higher VGS increases ID, but it has little effect in GM. So we are going to waste power. If you are going to increase VGS, you are increasing ID without increasing the transconductance. If there is no increase in transconductance but increase in ID, then the power is wasted because conductance remains constant. So power is wasted. No question of using this. Okay, this shows you are taking that equation. This shows you the current versus voltage curve or the IV characteristic curve for a 0.18 micron device. Now, if you look at this device, W by L is equal to 1.8 micron by 0.18 micron. That is how you define this device. 0.18 micron device means W by L is equal to 1.8 by 0.18. So L is equal to 0.18 micron. That shows that it is a 0.18 micron device. W here is 1.8. This is a MOSFET. Now, if you look at this, on the x-axis we have the gate source voltage. As we keep on changing the gate source voltage, the current is increasing ID, or the then current keeps on increasing. Look at this device. Look at this characteristics. The first portion is where there is no change in current. Current remains constant if you keep on increasing the voltage. So that is from 0.4 or 0 to 0.6 volt. In that range, it is not changing. After 0.06, it is starting to increase. This portion is called strong inversion or quadratic inversion. because in this portion 0.6 to 0.8, in this portion you can see the curve is nonlinear. It is like a parabola. It is parabolic in nature from 0.6 to 0.8. You know, parabola equation is y is equal to x square. So it means it is quadratic in nature. So in this portion 0.6 to 0.8, the inversion is strong. Below 0.6, the inversion is weak. Then after 0.8, you can see the curve is linear. Since the curve is linear, which means we have reached the velocity saturation. So on this device will work better with strong inversion in the range 0.6 to 0.8. So VGS should be between 0.6 to 0.8. If VGS is below 0.6, we have a weak inversion, it will not work properly. If it is above 0.8, velocity saturation has occurred, it will not work properly. This is the same device, only the curve has changed. Here what we are seeing is GM versus voltage. So the transconductance versus voltage. There we saw the current ID versus voltage. Here you can see the transconductance versus voltage. Now here you can see that in this range, in the inversion range, weak inversion range, and in the strong inversion range, both the weak inversion range and strong inversion. In the weak inversion range, the transconductance is varying. It is changing very fast. Small change in voltage gives a large change in transconductance. It is almost linearly increasing in that range. But after that, the increase is non-linear. From 0.6 to 0.8, we have the strong inversion. Then after 0.8, it again saturates. So because of saturation, GM is almost going to constant. So this range is saturation range is not desirable. Power is lost. That is what it shows. This is another example, GM versus current density. So current density is in the x-axis, GM is in the y-axis. You can see as you increase the current density is increasing above 300. The current density is increasing, but the GM is not increasing. GM is remaining almost constant. Initially GM is increasing, transconductance is increasing. After some time it remains constant. Current density IDEN. How do you define current density? Current density is ID per W. So ID by W, ID by 1.8 micron. Here in this case, ID by 1.8 micron. So this current density is remaining constant. Since current density remains constant, our transconductance remains constant with increase in current density. So those values of current density for which it remains constant is useless, and there you are not going to get any power. The power is wasted. You are giving more current, you are giving more power, but that is wasted because it is not affecting the transconductance. Now, equipped with this knowledge, how are we going to design the amplifier? What are the points, salient features which we should consider when we are going to design the amplifier? First is, it is not accurate to assume that there will be square law behavior by the device. Square law behavior means y is equal to x square in that form. There the IV characteristics will not follow y is equal to x square. That is square law. So it is completely inaccurate. Mostly it is very inaccurate if you assume that there will be a square law device. As we said, ID is equal to VGS square, quadratic function of VGS. That assumption is not correct. First, you don't take that assumption. It will be inaccurate to take that assumption that we have seen. Now, what we'll do is we'll introduce a numerical procedure based on simulated GM curve that we have seen for a transistor. Look at the transconductance. For the transconductance, you know, GM is equal to differentiation of ID with respect to VGS. So once we differentiate that, we get differentiation of WIDEN, because ID is equal to WIDEN. What is IDEN? It is current density. As we define, current density is equal to ID by W. Since current density is equal to ID by W, therefore ID is equal to W into current density. So here we can write d by dVGS, or differentiation with respect to VGS of W into IDEN. Now W is a constant, take that outside. So W into differentiation of current density by VGS at I density. So I density is constant for a given I density. Now here you can observe one thing. If we keep the current density IDN constant, then GM scales directly with W. So IDN, if you maintain that to be constant, then GM will increase as you increase W. GM will decrease as you decrease W. That is clear from this equation. Now this is again GM that is independent upon the bias. So whatever bias you use, it is independent upon bias. If it is independent upon bias, then we can relate this GM with the different widths. It is depending on width that we can see. So it is a function of width and it is a function of the current density. So GM is a function of width and current density. So GM function of W and current density, that we can write as W by W0 into GM as a function of W0 and current density. Now, what is W0? W0 is for a given value of this W, or a standard W. If you take a standard W as W0, so with that we can say GM W I density, or GM is equal to W by W0 into GM W0. GM W is equal to W by W0 into GM W0. That we can always say. This you can also find out from the equation for GM. GM is equal to W dIDN by dVGS. So GMW is equal to this. GMW0 will be W0 dIN by VDGS. Take their ratio, GMW by GMW0 is equal to W by W0. So from that also we can get this. Okay. Now let us look at a numerical design procedure for resistor amplifier. So we are designing the amplifier using resistors. So you can see the circuit here. On the right hand side is the circuit. You can see the two resistors that are used in the difference amplifier, design of the difference amplifier. So the two resistors are there. Difference amplifier is M1 and M2 are the two amplifiers which are the difference amplifier. From that you are giving two I bias to the M6, then alpha I bias to M5. Difference amplifier, you know, B in and B in cross, B in minus, because they are difference amplifiers. Anyway, what we'll do is here we will set gain and swing, single-ended swing. So we'll set gain and swing here. First, we'll set gain. So GM into R is equal to A. That we know that transconductance into resistor, a resistor that we are using for biasing. So that is equal to A, or the amplification. A, or the amplification or gain, is equal to GM into R. Use that rule or use that equation for gain. So GM into R is equal to A. GM is a function of W and I bias by W. I density is I bias by W. Similarly, VSW is swing, voltage swing. So swing means voltage varies between, suppose plus 1 to minus 1 or plus 1 to 0. So that is what is voltage swing. Peak voltage, the peak value and the lowest value, maximum value and the minimum value. That is what is swing. So VSW is equal to 2 times I bias into R. So 2 I bias into R is the voltage swing. We know these two equations. If we know these two equations, then from these two equations eliminate R. If you eliminate R, then we will get A divided by GM is equal to VSW divided by 2 I bias. So from that we will get GM is equal to 2 times A by VSW into W into I bias by W. So we have got an expression for GM in terms of A gain and in terms of swing VSW. So that we get. On that into W into I bias by W. I bias by W is also ID saturation. So that is I density. I bias by W is I density. That also is correct. Now, on the next question is, once we get this, can we relate GM, this equation to a GM curve taken from a device of width W0, standard width W0. If you take a standard width W0 for that GM curve, can you relate this formula? So let us see whether we can do that or not. We know this, the first two equations we have already seen. GM W I bias by W is equal to 2 A by VSW W into I bias by W. This is the equation that we saw, last equation that we saw. Then GM W I density is equal to W by W0, GM W0 I density. This equation also we saw when we found out the equation for GM. So these two equations we know. Now if we know these two equations, in the first equation, substitute the second equation. For GM, substitute the second equation in the first equation. So if we substitute that, we will get W by W0 GM as a function of W0 and I bias by W. That will be equal to 2 times A by VSW W into I bias by W. So from that, from both the side, left side and right side, W can be cancelled out easily. So once you cancel out W and multiply both the sides by W0, then we will get GM into W0, GM of W0 and I density. I density is equal to I bias by W. So GM of W0 into and I density is equal to 2 times W0 A by VSW into I density. So we can relate this equation. So this expression is allowing us to design the resistor loaded amplifier based on the GM curve of a representative transistor. So if you know any representative transistor of volt W, based on that GM curve, we can design it is possible to design a resistor loaded amplifier. Let us look at an example here. GM W0 I density is equal to 2W0 A by VSW I density. This equation we saw just now. Now assume that L is equal to 0.18 micron. Use previous GM plot. W0 is equal to 1.8 micron. The same GM plot we are using. So on the x-axis we have current density, on the y-axis we have transconductance. Then when we take gain is equal to 1, A is equal to 1, the current density is equal to 250 microampere per micrometer, that you can see. Here A is equal to 1, draw a line for A is equal to 1, gain is equal to 1 line, draw it. If you draw that line where it crosses the red curve, from there drop a perpendicular to meet the x-axis, it will meet at around 250 microampere per micrometer. For gain is equal to 2, draw the second curve, A is equal to 2 curve. So for gain A is equal to 2, current density is approximately 115. So 115 microampere per micrometer. So you can see that from this we can see the current density is reduced as the gain is increased. If you keep on increasing the gain, the current density will keep on reducing. Now with this we can also say, if we have we know the current density, that will allow us to design the amplifier. Remember this, VSW, the swing is equal to, swing voltage is equal to 2 times I bias into R. Free parameters are W, with is a free parameter, I bias is a free parameter, R is free parameter, provided L is assumed to be fixed. So all these three are free parameters. Free parameters means we have control over these parameters. Now suppose the I density is equal to 115 microampere per micrometer. This will give us a swing of 1 volt. We are going to get a swing of 1 volt, gain of 2. These are the two things that we require. Gain of 2 we have seen. Gain of 2 gives us I density is equal to 115 microampere per micrometer, that we have seen in the previous slide. Now choose I bias is a free parameter, so choose I bias to be 300 microampere. If I bias is equal to 300 microampere, then I density is equal to I bias by W, which means W will be 300 by 115. Because I bias is 300 microampere, I density is 115 I bias is 300 microampere and I density is 115 microampere per micrometer. So therefore W will be 300 by 115 micrometer, that will be 2.6. So that is 2.6 micrometer. W is equal to 2.6 micrometer. So W we have got. Once we fixed I bias, we now found out what is the W. Then swing. VSW, that is equal to, the swing is equal to 2 times I bias into R. Then we know what is swing. Swing is equal to 1 volt. So for that we put 1 volt. So 1 is equal to 2 times I bias into R, or R is equal to 1 by 2 times I bias. So 1 by 2 I bias is 300 microampere, which means 300 into 10 to the power minus 6 ampere. So R is equal to 1 by 2 into 300 into 10 to the power minus 6. So that is equal to 1.67 kilo ohm. So once we fix I density and I bias, once we fix I bias for the given I density, we can find out what is W and what is R. So
answer.
Hello.
सर कंटिन्यू करंतु आप.
Now you can note that instead of choosing W or R, we can calculate other parameters. Instead, if you choose W or R instead of I bias, we can choose W. Then we can find out what will be I bias, what will be R. We can choose R, we can find out what will be W, what will be I bias. Follow this, the same procedure. Now question is, suppose we are choosing I bias. How I am going to choose I bias for high bandwidth? The main thing is, in the design, the main focus is on designing a high-speed circuit. How to get high-speed circuit? This circuit should have, the amplifier should have higher bandwidth. The more the bandwidth, the more the speed. So to get high-speed circuit, we require a high bandwidth. So broadband amplifier design. So for a high bandwidth, how we are going to choose the I bias? So what we will do is here, first pick the current density just below velocity saturation. That is the point. Main point is pick the current density just below the velocity saturation. Because once you reach the velocity saturation, we have already seen, once we reach the velocity saturation, then GM is not going to be affected by increasing IS, so no point going beyond the velocity saturation. Just below, so stay just below velocity saturation. That gives us current constant current density. Size of the transistor can also increase to keep size of C in and C out, because they are increasing relative to C fixed. So we have to find out a relationship between C out, C in and C fixed. As we increase I bias to achieve the highest bandwidth, size of the device means on the L and W. Size of the devices, that is, choose the value of I bias. First you choose the I bias so that C in plus C out, they will dominate over C fixed. That is the first point. C in plus C out should dominate over C fixed. If you are going to increase I bias to achieve highest bandwidth, this is one requirement. However, when you go for C in plus C out is equal to C fixed, this is roughly the point of diminishing return, because the bandwidth improvement after this point becomes marginal. There will be increase, but it will be marginal. But although there will be a small increase, but it will require high power, and area continue to grow proportionately. Area of the device, that will which means size of the high power means size will keep on increasing. Therefore, C in plus C out is equal to C fixed. This is the most efficient point when you design. Design it in such manner that C in plus C out is equal to C fixed. You don't have control mostly over C in C out. So C in plus C out, those will be depending on device. You have to fix the C fix, so that you are going to join, so that you can fix. Always choose C fix is equal to C in plus C out. Now let us look at resistor loaded amplifier for the devices which are made up of on-silicided poly. So those devices, we have seen these equations, so I am not going to continue with this equation. C total is equal to CPV1 plus CRL by 2 plus CGS plus K COV2 plus C fixed. K is a Miller multiplication factor. So here we decide that this is the fastest non-enhanced amplifier. So beyond this, can we go beyond this amplifier? Can we enhance the bandwidth beyond this? That is the question. To go beyond this, we have to look at the following: reduction of Miller effect on CGD, short series and zero peaking, distributed amplification. These are the three things in the amplifier that we distribute. Let us start with Miller effect. CGD is significant compared to CGS. So capacitance between gate and drain is comparable to the capacitance between gate and source. It is significant. So if you are considering a 0.18 micron CMOS device, CGD is about 45% of CGS. Under that condition, the input capacitance calculation, as you know, is using the Miller effect. The input capacitance calculation is Zin is approximately equal to 1 by S into CGS plus CGD into 1 minus AV. You know, S is equal to J omega. So we are not writing J omega, we are writing S. So that you can write as this is equal to 1 by S into CGS, take CGS common. So that is 1 plus CGD by CGS into 1 plus GM RL. So now from where we get this GM into RL, you know the expression for AB, just put the expression for AB. So AV into GM into RL into CGD by CGS is equal to minus AV. That is AV is the amplification, and Y minus AV, from where we get this minus sign, that is because the change in the phase. So based on that. Now for 1/8 micron CMOS, if you look for gain 3, input capacitance is almost triple over the CGS. So they didn't say there, here just put gain is equal to 3, AV is equal to 3. That gives you Zin is equal to 1 by S into CGS into 2.8, which is approximately 3 times more. Now we have to reduce CGD. The impact of CGD is to be reduced. So that we can do using a Cascode device. To reduce this, we will use a Cascode device. So you can see what is Cascode device. In the Cascode device, you join the drain to the source. So drain and source are joined. When you drain to source is joined, it is not series. It is drain to source joining. So once you use a Cascode device, the purpose of Cascode device is to lower the gain. It will lower the gain seen by CGD, not the total gain. Total gain will remain almost same as the non-Cascode amplifier, but the gain seen by CGD of the M1, that will be lowered when you go for a Cascode. How it happens? Because AV is approaching GM1 into 1 by GM2, which is approximately equal to 1. When they are in cascaded, then the gain is GM1 into 1 by GM2. When M1 is in cascade with M2, so GM1 into 1 by GM2 is the gain. So AV is approximately GM1 into 1 by GM2. Since M1 and M2 are same devices, therefore GM1 into 1 by GM2 will be approximately equal to 1. So if that happens, AB is approximately 1, then Zin is approximately equal to 1 by SCGS into 1 plus 2 CGD by CGS. Then for 0.18 micron CMOS and total gain of 3, the impact of CGD is reduced by 50% here, because Zin now becomes 1 by SCG into 1.9. So instead of 3, now it has become 1.9, which is around 50% reduction. Issue here is cascading will lower the achievable voltage swing. Voltage swing will be limited. Only that is the issue. Except that you can do this. So with this, we will take a break, lunch break. After the lunch, at 2:30 we will start. କେତେ ପେଜ ଦବା ଦେଖିବେ କେତେ ପେଜ ଦବା ହଁ